Okay, welcome to INDS 3050 Intro to Metals, lecture number 2 on cast irons. And okay, so hold on one sec. So iron has a chemical symbol of Fe. Has a melting point of about 2,800 degrees Fahrenheit, so very hot. And that's why back in the olden days they had trouble melting iron. So a lot of the processing for iron was done in the red hot or solid state. And it wasn't until much more modern times, that we could actually melt steel. Density, very high density, about 8 grams per cubic centimeter. So 8 times the density of water. Aluminum somewhere around 2.7, something like that. So almost triple the density of aluminum, but also in some cases about 3 times the strength. So the important thing is the strength to weight ratio, not so much the actual strength itself. Okay, so but if iron does not have any alloying elements, it is not very strong or hard. You can almost scratch it with your thumbnail. So iron is produced by taking different types of iron ores, and the two main ones being hematite and magnetite. You might have seen hematite. You can get little rock-looking things that are hematite. Magnetite is both of them are hematite is what you see is red rust on your car typically, but if it's in kind of a lump form, it's kind of a silver, a gray color sort of. And then there's some other types of iron compounds that are sometimes mixed in with the ore. Siderite, pyrite, which you've heard of as fool's gold, iron sulfide, and limonite. But mostly we want to have these two top ones because they're much higher percentage iron. Okay, so there is a movie that has to do with steel making. The first part of it is a blast furnace. So if you wanted to, it's in the assignments to watch that. If you wanted to watch the first part right now, it's not a bad idea just to get an idea of what I'm talking about, but it's just the part on the blast furnace that you could watch at this point. Okay, to make iron, we have to take iron ore and somehow reduce it. And the word reducing means stripping electrons away, or actually what you're doing is you're taking, in this case, Fe2O3 or Fe3O4, and you're ripping the oxygen off of it. So what we need to do is we need to find something that is, let's say, has more affinity to the oxygen than the iron does. So you're going to strip off that oxygen from the iron, and then we'll be left with the iron itself. Okay, so how do we do that? Find something that wants it more, and the likely case is carbon monoxide. So carbon monoxide, and it has to be at a high temperature. So we actually take carbon monoxide at high temperature and put it in contact with the iron ore, and it's called reduce. We reduce the iron to iron itself, iron oxide to iron itself. So let's see how that's done in the blast. Okay, so let's take a close look at this picture here. We have, we're going to charge it through the top. So we're putting in the top here, there's a little bell here that helps to hold the material back and allow the exhaust gases to escape. So this is called a counter current reactor. What does that mean? That means that the solids are moving down in this furnace and the gases are moving up. It's a very efficient furnace. In fact, here we have high temperature air or oxygen being injected and out here we have exhaust gases at a much lower temperature. And so all of the heat that's produced down here gets transferred and preheats the material coming in. So as the material drops through the furnace and the molten iron and slag is taken off, then more material is added in the top. So this is a continuous process. Typically, these blast furnaces will run for maybe 10 years before they actually turn them off. You have probably seen these if you've ever traveled on the Skyway around Chicago going east towards Michigan. Okay, so if you take the Skyway, it's a toll road, and if you when you go by, what you'll see is really, really tall buildings, or not buildings, like structures, like big tubes, and you'll see a U.S. Steel sign or something like that. So the blast furnaces, I think there's 3 or 4 at U.S. Steel as you go by, and they're pretty impressive actually. 200 something feet tall. Okay, so you can't miss them while you're going by Gary, Indiana. Okay, so you're going around the bend and you're going by Gary, Indiana. So what else is in here? We're putting layers of iron ore, and then we're putting coke. Okay, so normally I have some coke that I pass around to you, but coke is essentially a coal that has been turned into just basically pure carbon. Okay, and they do that in a special furnace, and then the limestone is added. So a small percentage of limestone is added, and what that does is it actually combines with the other rock materials that are in there that come in with the ore and create a liquid slag. Normally, at the temperatures that this reactor is going on, the rock-like materials make kind of like a magma, which we call slag, but the melting temperature of that slag is really important. We want the melting temperature to be low so the slag can be taken off as liquid instead of a gooey mess that it can be sometimes. So limestone lowers the melting temperature of that slag, so therefore we can take it out the bottom of the furnace as a liquid. Okay, so we have iron ore and then coke layers and then a little bit of limestone mixed in there, and we alternate those layers and they go all the way down to the bottom of this furnace. So this is probably 150, 200 feet tall here. The largest one that we've been to in Germany it does 500 tons an hour, and the inside diameter is 55 feet. So these are huge furnaces. It's lined with a brick material that is magnesium oxide or something like that keeps, it's an insulating material, okay? And it can deal with the heat and the slag. Okay, so what happens is, in this area here, we have combustion. It makes carbon dioxide and carbon monoxide. The carbon monoxide then reduces the iron ore here, and as it comes down, eventually it melts, and we have molten iron down the bottom. We take that off through a hole in the bottom of the furnace, and then up here we take off the molten slag because it floats on the surface. Over here we have something called a tuyer. Weird word, but we have 3,000 degree air being injected, air and oxygen being injected into and combusting, and that's generally what's happening in the furnace. There's a hearth section, a boss section, a stack section, and then there's the top of it. Okay, so you should probably understand the parts of this blast furnace. You might see them again. Coke, iron ore, limestone, and oxygen and air are entered in here. So generally, we're going to put about 2,000 pounds of, in order to make a ton of pig iron, we're going to put 1 3/4 tons of iron ore, because in the iron ore is some other materials like rock, like silica and things like that, and that comes off as slag. Also in the iron ore, Fe2O3 is a bunch of oxygen, and that oxygen has to be stripped off, and it weighs something, of course, when it's in its ore form. The fuel is coke. It takes a half ton of fuel per ton. And then flux is a quarter ton. So 2 tons of air, you don't think of air as weighing much, air and oxygen, but 2 tons of air and oxygen go into that furnace to make 1 ton of pig iron. Also 10,000 gallons of water coolant goes in there. You'll see really big retaining ponds for around Gary, Indiana, where they cool that water. Okay, let's look at some of the chemistry of what's going on. Carbon burns to make carbon dioxide and heat. Okay, and there probably is some CO2 that gets produced as well. But what happens is there's coke inside the furnace. So as that carbon dioxide goes up through the furnace, there's warm carbon in there, and it converts it back to carbon monoxide. Okay. So carbon monoxide reduces, here's the chemical reaction, Fe2O3 or Fe3O4. It would have a slightly different balance. But essentially we're stripping this oxygen from the iron by CO2, because CO at that temperature, let's say above 1600 degrees Fahrenheit, goes to iron, 2 irons and 3 CO2. So out the top of the stack goes carbon dioxide. Okay, so we just need to plant some trees and we'll get rid of that carbon dioxide. End products of the blast furnace, we have a 1/3 ton of slag that comes out. We have 3 tons of furnace gases, carbon dioxide, nitrogen. Now nitrogen just goes in and goes for the ride, so that's why we try to add oxygen to decrease the amount of nitrogen that has to get heated up in the furnace, because it does take energy. We have then pig iron. Okay, they also call it, I think, hot metal, or at the steel making plant, but it's really pig iron. Especially if you put it into ingots and then sell it, you can actually sell it in this form. So pig iron is sold to foundries that make cast iron, but pig iron is used in the steel making process also. Okay. So we have like 4% carbon, a couple percent silicon, some sulfur, manganese, phosphorus, and a lot of this needs to be removed in order to make steel out of it. Or cast iron needs to have some of the sulfur and phosphorus removed. Okay. So generally we have the cast irons. We have wrought iron, which is old-fashioned type of stuff that we don't really use anymore. And then we have steel, different kinds of steels. Now there's literally thousands of kinds of steel. But what we're going to talk about today is mostly the cast irons. And the difference between cast iron and steel is cast iron has silicon, I would remember that, and graphitic carbon, so much higher carbon contents, so high carbons and silicon, where steel has low carbon and really doesn't contain much silicon at all. So we're talking about 2% in cast iron and maybe 3.5% carbon, and in steel we're talking somewhere around, below 1.5, 1.7% carbon and almost no silicon. Okay, wrought iron is basically pure iron with slag stringers. Back in the old days, we had a lot of trouble being able to process steel as a liquid. Okay, so wrought iron was a product that was made, and it has essentially pure iron, no carbon in it, with a little bit of slag, and it's made by a completely different process that we're not going to really go into. But stopped pretty much making it around 1910, 1920, and steel production started in the late 1800s, at least in quantities that made it economically viable. Okay, what is gray cast iron? Gray cast iron is essentially pig iron that we kind of purify a little bit, and we can remelt the pig iron, and then we put some steel scrap in there and maybe some other cast iron that we got from scrap from, let's say, radiators and old equipment, things like that that are no longer useful that we recycle. We put them into a furnace called a cupola furnace. Cupola furnace looks exactly like a blast furnace, but instead of putting iron ore in the top of it, we're putting scrap materials in the top of it. And then we're putting the coke and limestone and all that kind of stuff. And out the bottom of that furnace comes iron. So Neenah Foundry has one of these. Wapaka Foundry, or actually Neenah Foundry has 3 of them. Wapaka Foundry has a whole bunch of them. And it's mostly the most efficient way of making cast iron. We can also melt it in an electric induction furnace and a couple other ways, but those are the 2 big ways we do it. We have electric induction furnace in our lab. We also do have a cupola furnace that we run from time to time. Okay, so what does it have? Let's say generally around 3.5% carbon, 2% silicon, somewhere 1.8, 2% silicon, some manganese in there, maybe not always this high, sometimes a little bit lower than that. And then sulfur and phosphorus, you can see, is at a lower level. It produces a cornflake-like structure. Okay, so I'm going to have to turn back here. So imagine that you took some milk and your cereal cornflakes. Maybe you don't eat that, but let's say you had some, just for argument's sake. And then you put that in a bowl, you put that into your freezer, and you freeze that whole batch of flakes and milk. Now what's going to happen is you're going to get ice, essentially, and you're going to have little disruptions in there where the flakes are. Now if I took that out of the freezer after it was completely frozen, and I could somehow magically do this, I would make a round bar out of it, okay? I would have to have a very cold lathe, maybe up in the North Pole or something like that, and I would turn a bar in a certain diameter. And if I were to take and I would pull on that in tension, what you can imagine is ice is very strong. I race ice boats. The ice that you need to stand on is about 1 inch thick. To be able to ice boat, 2 or 3 inches thick. To drive your car on, 6 inches. So ice is very strong. And so if you start pulling on this rod with ice and cornflakes, you can imagine the cornflakes are kind of a weak point in there. In fact, it's like a crack, and if they're oriented in the right direction, they'll kind of fracture right along that flake. So that's what cast iron is. It's essentially steel with silicon in it. And then it's got these disruptions, and those disruptions are actually graphite. Because there's so much extra carbon in there, the carbon can't stay dissolved, so it forms like actual graphite, like that's in your pencil. Okay? Now, if you've ever taken a lead pencil, they call it lead, but it's actually graphite, and you've broken the tip of it. Of course you have. If you have one of those mechanical pencils, the tip breaks all the time. Graphite's not very strong. So the graphite is just like the cornflakes in the frozen milk, and therefore the structure fractures relatively easy in tension. Now what if we put that same material in compression and we try to push it together? All those cracks are just getting pushed together. So a weird thing about cast iron, it's 3 to 5 times stronger in compression than it is in tension. It's a weird material that way. That doesn't have the same properties in one versus the other. So cast iron a lot of times is used for things like where a bridge is resting on a reaction point, they call them, and the bridge has to be able to expand and contract, and one of the reaction points will have an actual little a pivot on it, and so this thing's resting on this cast iron pivot, so that when the bridge gets longer, the pivot tips one way or the other way, and it allows the bridge to expand and contract, and the material in that situation is under compression. So what does cast iron actually look like? It looks like this. If we take it under a microscope, and the way we do this is we take our sample and we of cast iron, we cut it in half, we polish it, and then very, very fine polish with abrasives, and then we look at it on the microscope. Now, it's a special microscope that it can't see through the part. It uses a reflection to look at the structure. So if you take my metallurgy class, we'll be using that microscope. And if you look at cast irons, it'll look something like this. These gray areas here, these are darker areas here, that have long, linear shapes. It's a 2D cross section through a 3D structure. So they really look kind of more like potato chips that are all glued together. And this is at it's just a very high magnification, like 50 or 100 times magnification. Okay. So what is the advantage of this material that's not very strong in tension but good in compression? It also has great vibration dampening, and it's cheap. So essentially we take pig iron, we purify it a little bit, and then we pour it into a mold, and now we get this structure. It's got excellent castability. It's really fluid. It'll flow into the molds. It's got good machinability, which means I can cut it. The machine tool moves along and cuts through these little graphite areas, and the chips break off, and it's really easy to machine. It's great in compression, and here's the weird thing, is that if you're using it in a car engine, most engines, the actual liners, the cylinder bores, are made of cast iron. Even the rings that go around the piston are made of cast iron. Why? Because it has great lubrication properties. One of the reasons is all those little places where there's graphite exposed to the surface, when you machine it, it creates a little crack that's open to the surface. Oil can get down in that little crack, and it stays in there by capillary action, and so it's really good for lubrication. And so cast irons, gray cast iron, is the best thing to use for an engine block. When you make an aluminum engine block, you actually put those cylinder liners are usually cast iron. So I would just rather make the engine block out of cast iron and make it lighter. And there's ways to actually do that. We'll talk about them a little bit later in today's lecture. So cast iron's pretty cool. Let's see what the disadvantages of gray cast iron are. So low to medium strength, 20 to 50,000 pounds per square inch in tension. Okay, so we talked a little bit about steel maybe last lecture. Steel might have 60,000 pounds per square inch, like a weak steel. So it's not as strong as steel. And it's got low impact resistance. You start hitting your engine block, if it's cast iron, you start hitting it with a hammer, it might actually crack. So it's not used in an application where we want to have impact resistance. Okay, so here we are using those properties that you learned last week. Okay. White cast iron, what is that? So gray cast iron, by the way, I forgot to mention this. Gray cast iron is called gray cast iron because the graphite, when you fracture it and you look at the fracture, the graphite makes the surface look gray. So there's all those little flakes that are exposed. So instead of being kind of shiny silver in that fracture, it looks gray. So if I take the same cast iron and I cool it very quickly, or I change the composition slightly, maybe I lower the carbon a little bit, what happens is instead of graphite forming when it cools, it forms iron carbide. And if you ever heard carbide before, you probably know that it is very hard and brittle. So much harder than cast iron even, and even much more brittle. So white cast iron is molten cast iron, cooled quickly, or the carbon content lowered. That's what you want to do in order to guarantee that you white cast iron. Usually you use thin sections on your cast iron. So 2 to 3.5% carbon typically, whereas regular gray cast iron might be more like 3.5 or maybe a little bit more. And we sometimes use white cast iron in the first step of making other types of iron as well. I'm actually doing a project right now with a company that does that makes castings that are for wear-resistant applications. So some applications that you could think of for white cast iron would be a pulverizer for pulverizing coal. So I don't know if you know this, but when your power plant uses coal, it has to powder the coal first, and in order to do that, they have basically a big track with huge steel ball bearings going, or white cast iron ball bearings going around. So I work with a company in South Africa that makes really hard white cast iron balls. They're probably around 2 to 3 feet in diameter, and it makes a track that's about 15 feet in diameter that they run in. And so you put coal on the surface of that track. It's just basically like a trough like this, and then these balls run it over. And they have an upper and a lower cage that basically turns this thing around and it crushes the coal. Then that powdered coal then goes to the burners to get used for burning and producing heat, which produces steam, and then they generate electricity. When I was living there, probably on a daily basis, the power went out because they don't have enough coal to power the power plants, which has to do with government corruption, but that's a whole nother story. Okay, so what does white cast iron look like under the microscope? Looks something like this. Now, wow, that's kind of a lot different than the last thing, and essentially they're the same thing, right? So white cast iron looks like this. All this white stuff is the hard part. So it's iron carbide, very hard. And the dark stuff essentially is steel, okay? So in the last case, it was steel with graphite, and in this case, it's steel with this white hard carbide material, okay? So if you take a hardness on a Rockwell hardness tester, like you saw in your heat treatment lab that you're doing, this is only Rockwell 31, which is not very hard. Actually, hardened steel is Rockwell 65 or so, or 63 maybe, something like that. Whereas this is 31 because it's an average hardness of all this. But what happens typically is if you put this in a wear situation, all the dark areas wear back a little bit, and then you're left with all these areas on the face of it, and therefore it's wear resistant in that case. So they use it for concrete and things like that. So it cannot be machined typically by regular machine tools. You have to grind this material. So what you try to do is cast it really close to its final shape and then maybe do a little bit of grinding. Okay, malleable iron. Now, malleable iron is essentially white iron that we've done a heat treatment to. And the weird thing is that back in the old days, before 1950, if you wanted to cast iron and then have it be ductile, in other words, actually have some elongation and tension before it failed, and unfortunately they call it malleable iron. Malleable iron is actually both malleable and ductile, so I know it's confusing, but malleable iron is actually it's a very ductile material that you can use for, I don't know, they used to use a lot in automotive applications. The fittings for black pipe, when you make black pipe, it's malleable iron. They still use it, but that's about it. I may have talked about it in the last video a little bit. So what is it used for? Oh, how do we do it, I mean? So what we do is we take our white iron, we put it in a furnace. So usually they had these big ceramic boxes. They would put the castings in there and then fill them with sand just to keep things from warping around and oxidizing. They would put it in the furnace for 120 hours at, I don't know, somewhere around 1800 degrees, 1500 degrees Fahrenheit. And then what would happen is those carbides would break down and they would make little nodules of graphite. So essentially, you're making cast iron, but instead of it being flake shaped, it was more or less, okay, so now I got to use another, let's say another analogy. So if you were to take grape nuts, which is, I don't know if you've ever seen that even, but it's kind of like granola and milk, and you froze that, and you put it, and you make a bar out of it, and then you pull it in tension. What you can imagine is that those roundish blobs of granola in the ice are going to be less detrimental. They're not kind of cutting the surface or making a crack for a crack to form, and so they're basically going to make your part more ductile. Okay, and generally in tension and compression, it was relatively good and ductile. Okay, so we can have about 35 to 65,000 pounds per square inch. So, and that's the yield strength, and 50 to 75,000 pounds tensile strength. So it's actually decently strong, and 10 to 20% elongation before failure. Okay, and so what that means is that if I put this in a tensile testing machine and I pull on it, just like I did with the wire the other day, if I pull on it, it will elongate and then it will fail. So you get a little bit of warning of when it's going to fail. Okay, so 10 to 20% elongation is pretty good. So here's what it looks like under the microscope. So here's our temper carbon nodules, they call them, and so essentially these formed from the last weird white cast iron microstructure that you saw. So we had, okay, this is the amazing thing about metallurgy. So the casting looks the same on the outside, but it went from being super wear resistant, hard and brittle, to not super wear resistant, but tough and ductile. And that was just by putting it through a heat treatment. Okay, so again, that's why the people in ancient times thought it was magic, because you just basically heated and cooled things, and they somehow got completely different properties. Okay, relatively high stiffness. The elastic modulus is high, is what I'm talking about there. We talked about that in the last class. Remember, this elastic modulus is the slope of the stress-strain diagram. It has good impact resistance, but the problem is it's pretty expensive because of that long heat treatment. So if we could make a ductile material without having to spend all that time in that heat treatment furnace, it would be great. And then along came ductile iron. Ductile iron was invented by Keith Mellis in around 1950, and then he worked at the International Nickel Company. Okay, so imagine if you took Cocoa Puffs and milk and you froze them. Okay, so Cocoa Puffs are completely spherical. And now if I take and I freeze that, and I take that out and I make my tensile bar, and I pull on that, what happens? Well, the cracks that go kind of across it, every time they hit one of those spherical holes with graphite in it, it tends to blunt the crack. In other words, if you know anything about, let's say, cracks propagating, you gotta if you had a windshield and there's a crack going across it, and you could drill a hole in the end of that crack, it would stop that crack. Okay. In fact, I think they kind of do that when they fix your windshield. They put plastic in it. But I have a plexiglass piece on my popcorn maker, and it has a crack going across it. I just drill a little hole in the end of it. It was propagating a little bit each time I opened the door. So once I put that in there, it stopped it, and now it's been the same place for a really long time. Same thing in metals. A stopgap measure is to drill a hole at the end of the crack to blunt the tip, because otherwise you're concentrating all that force of that crack on one little spot. Okay, so what goes on in ductile iron is if you have a crack going through the part, it tends to hit these spherical. It's a little different because it's hitting a sphere and it's a horizontal crack, but it tends to want to stop that crack. So ductile cast iron is very ductile, and it's also ductile in the as cast state. Okay, so how does that happen? How do we, by the way, cast iron's been being used for now, I don't know, several thousand years. I think up to 2000 BC or something like that, they think. And so with that long of a history, it took us that long to figure out that if we just add some magnesium or something to remove the sulfur to a really, really low level, when it cools down, the graphite, instead of forming flakes, will form spheroids. It's kind of, this is one of the best inventions since man started figuring out, digging in the dirt and finding iron ore and playing around with it. So it's pretty amazing. So the properties can be controlled from 40 to 70,000 pounds per square inch yield and 60 to 100,000 pounds per square inch in the as cast condition. But as you go up in strength, so if you have 100,000 pounds per square inch, you typically only have 3% elongation. If you have 60,000 pounds per square inch, you have near 20% elongation. And these are the minimum numbers, by the way. 40, 70, 60, 100, those are the minimums. It might be, let's say your part is 120,000 pounds per square inch, but for that grade, the minimum is 100. And let's say I have 4.5% elongation instead of 3. That's good. It has to be a minimum of 3. Okay? Now, the crazy thing about ductile iron is that you can actually heat treat it and double these properties. And so Henry, the person that is helping in the lab, he actually worked at a company that was doing heat treatment on ductile cast iron. And you could take a ductile cast iron part and get a better strength to weight ratio than aluminum. So that's pretty amazing. We'll probably spend a little bit of time on it at some point in this class. So here's what it looks like under the microscope. We have spheroids of graphite with a iron surrounding matrix. Okay, relatively good elastic modulus, not quite as good as steel. The damping properties are not as good as gray cast iron because sound waves can travel through it a little bit easier than it can through with the flakes. And it has relatively good castability, but it shrinks a little bit more and it's not quite as fluid. So if I were to make something in ductile cast iron, it's going to be a little bit more expensive than the gray cast iron. And for an engine block situation, it's okay, but you'd rather, from a lubrication standpoint, you'd rather have the gray iron at the cylinder liners. So the disadvantage of this process of making iron would be it's somewhat hard to control the process. It's a little bit more expensive than gray iron, but it's pretty amazing stuff. Okay. The next kind of iron we're going to talk about is a composite of the two. And I don't even know what kind of cereal this would be, but compacted graphite iron, or CGI it's called. About 1970s we came up with this. We decided, well, if ductile iron's great for ductility and for strength, and gray iron's good for lubrication properties, but it's kind of heavy and we have to use a lot of it because it's low in strength. What if we made something somewhere between the two, and then we could make engine blocks that are much lighter but strong and have those almost the same lubrication properties that gray cast iron has. Now, if you look up CGI, the use of this is mostly in diesel engine blocks. So it's pretty amazing that this structure, and let's call it a coral-like structure, and this is in 3 dimensions. And by the way, this is under an electron microscope. So what they did was they took acid and etched away all the iron, and then we're left with the structure of the graphite, because graphite doesn't etch in acid. And so you see here that there's a couple little nodules maybe, but mostly it's this coral shaped stuff. How do we do this? Well, instead of adding magnesium to molten iron to get rid of the sulfur, we still do that, but we only add a certain amount. We control it to a level that will produce this structure that's halfway between the gray and the ductile iron. Okay, so the Germans call it vermicular, which means worm-like. So the vermicular structure between gray and ductile iron, it's a lot harder to control than ductile iron. It's used for engine blocks, and it's higher strength than gray iron. So the cool thing is you can get a similar or better strength to weight ratio in some cases in CGI irons than you can in fact, you could make an engine block, and let's say the whole engine, when we consider the engine block, the crank, and all those kind of things, at a lighter weight than you can an aluminum engine block in some cases. And for diesel, you need the high strength and high fatigue resistance because of the high compression ratios in diesel engines. Okay, so that covers the different types of cast irons. Now, cast irons are my favorite subject. So if you were to study something for a test or whatever, make sure that you know what all the difference of these are, and you know what they look like, what the microstructure looks like. And I think it's really important that you understand this stuff. Someday you'll probably design something and you say, like, you know, what type of material should I make this out of? Everyone's making everything out of aluminum, but you know something? I'm going to look at this cast iron and see which one of these things is better. You will probably save your company a whole bunch of money because these castings are going to be a lot cheaper than the aluminum castings, and they'll probably be have a longer service life as well. So that sums up cast irons. Stay tuned for the next lecture and homeworks on these same items.